Let us start by examining the architectural logic of vessel junctions from a macro to micro perspective. Explain the fundamental difference in the design criteria for preventing local plastic collapse between ASME Section 8, Division 1, and Division 2, Part 5 elastic analysis, specifically when evaluating heavy wall nozzle junctions.
Well, the primary distinction lies in how each code division handles the reality of localized stress. Division 1 approaches nozzle junction vulnerabilities through rigid empirical area replacement rules.
You are referring to UG 37.
Exactly, specifically under UG 37. It is essentially a volumetric accounting method. It dictates that if you cut a hole in a vessel for a nozzle, you must replace that exact volume of removed metal in the immediate vicinity of the cutout. It never actually computes the true localized stresses.
It just blindly replaces the mass.
Right. It assumes replacement equals reinforcement.
Hmm.
Division 2, Part 5, however, employs design by analysis, commonly referred to as DBA. This methodology abandons that volumetric assumption entirely and uses linear elastic stress categorization.
Break down that categorization for me.
It mathematically segregates the complex stress profile at a junction into distinct fields. So you have your local primary membrane components and your secondary bending components. It then verifies these specific fields against different targeted multipliers of allowable stress.
To ensure we are completely aligned on the physical mechanics here, when we talk about membrane stress, we are essentially talking about the raw, load-controlled stretching of the material right through its entire thickness, akin to a balloon expanding uniformly outward.
Yes, that is a solid analogy.
And bending stress, on the other hand, is a gradient. It is more localized, like creasing or folding that same balloon at a rigid pinch point.
Correct. That is an accurate physical translation. And because those two behaviors threaten the structural integrity in completely different ways, Division 2 categorizes them across a stress classification line, or SCL.
And where exactly is that drawn?
This line is drawn directly through the critical thickness discontinuity of the solid model. The local primary membrane stress your expanding balloon analogy represents the load-controlled response that must resist gross structural bursting from internal pressure.
Which is obviously a catastrophic failure mode.
Exactly. Because failure here is catastrophic, this stress is strictly capped at 1.5 times the allowable stress, or 1.5 S sub m. Conversely, secondary bending stress represents a self-limiting, displacement-controlled state.
Displacement-controlled meaning it's driven by thermal movement?
Usually, yes.
Mm-hmm.
It is typically driven by thermal expansion mismatch between the thick vessel wall and the thinner nozzle, or structural constraints at the hub. Because it is self-limiting, meaning the joint bends slightly and the stress relieves itself, it is capped much higher at 3 S sub m.
Let us play devil's advocate for a moment. Division 2, Part 5, Design by Analysis, requires expensive, computationally heavy finite element analysis. It demands significant engineering man-hours. It does. Division 1 simply dictates we weld on a reinforcing pad to replace the cut metal. Why take on the upfront costs and schedule delay of an FEA when Division 1 has historically provided thick, seemingly robust junctions?
Because in high-temperature refinery applications, throwing raw metal at a problem frequently creates a much more dangerous vulnerability. The assumption that thicker is always safer is a dangerous engineering trap.
A trap. Explain.
Well, if a structural engineering team relies on Division 1, or if they misuse Division 2 by misclassifying a localized thermal expansion stress at a nozzle junction as a primary membrane stress instead of a secondary bending stress, they are forced to over-design the nozzle neck thickness.
So they bulk it up.
Right. They add massive amounts of steel to satisfy that stringent 1.5 S sub m primary limit.
Walk me through the physical reality of that added mass. Why exactly does a thicker nozzle neck actively worsen the situation?
It comes down to thermal transients. Thick sections of metal heat up unevenly. The internal surface in contact with the hot process fluid expands rapidly, while the external surface remains relatively cool. The metal effectively fights its own expansion.
So it binds up.
Exactly. By artificially thickening the nozzle neck to meet a misclassified stress limit, you drastically increase the thermal stiffness of the junction. You create a rigid block of steel that cannot flex or distribute thermal gradients.
And what is the long-term result of that stiffness?
Instead of a safely bending joint, you engineer a brittle thermal response that actively worsens thermal transient stress tracking. That leads directly to accelerated fatigue cracking. Division 1 bypasses complex stress profiles by enforcing rigid geometric area buffers, while Division 2 isolates structural load-controlled membrane fields from self-limiting bending fields using stress categorization across an SCL.
I require quantitative field proof to back up this architectural logic. Provide a specific scenario where Division 1 methodology mandates a failure, but Division 2 Part 5 safely validates the physical reality of the design.
Consider the engineering of a 24-inch heavy gas oil inlet nozzle on a thick-wall hydrocracker vessel. If you run standard Division 1 area calculations, this design frequently fails on paper.
Due to the reinforcement boundaries.
Right. The code's tight reinforcement boundaries restrict where you can credit replacement metal, forcing the designer to add a massive, thick reinforcing pad. However, conducting a Division 2 Part 5 elastic finite element analysis reveals the true physical mechanics.
And what does the FEA show in this specific case?
The FEA demonstrates that the peak localized primary membrane stress across the correctly placed SCL is only 1.3 S sub m, and the secondary bending stress from the thermal gradient is 2.4 S sub m. Both of these localized values sit safely within the code's distinct limits.
So the pad is entirely unnecessary.
Completely unnecessary. The design is successfully validated as structurally sound without adding thick, detrimental reinforcing pads that would choke the thermal flexibility.
Are there execution vulnerabilities when deploying this finite element analysis? I mean, standard software can produce colorful stress plots that look authoritative, but garbage data yields garbage validation.
Absolutely. The most critical vulnerability in an elastic FEA under Division 2 Part 5 is the placement and alignment of the SCL. The software will calculate stress across any line you draw, but the code demands precision.
How precise?
The SCL must be oriented exactly perpendicular to the midplane of the wall section and positioned precisely at the region of maximum stress gradient. If a junior engineer misaligns or shifts the SCL slightly to artificially sample a lower stress region, the software will output passing membrane and bending values.
Which gives a false sense of security.
Exactly. This fundamentally compromises the structural validation, leaving the vessel vulnerable to sudden localized cracking during intense pressure cycles, all while the documentation falsely claims code compliance.
Understood. Let us pivot. You previously mentioned the 3 S sub m limit for secondary bending stress. Moving to another question regarding that limit, explain the mechanical significance of the shakedown to elastic action principle under ASME Section 8, Division 2, Part 5.
I can certainly do that.
And specifically clarify how it prevents progressive structural distortion in assets that heat up and cool down for decades.
Shakedown is a mandatory code-defined structural condition. It dictates that an asset is permitted to undergo a small amount of localized plastic deformation, actual permanent yielding, during its first few initial operational cycles.
Because of those secondary stresses.
Right, caused by those high secondary stresses we discussed, provided they remain less than or equal to 3 S sub m. During these initial cycles, the localized yielding actually develops a system of protective residual stresses.
Protective residual stresses. Elaborate on that mechanism.
Well, this internal shielding forces all subsequent operational cycles to track entirely within an elastic stress strain loop. The material effectively hardens and protects itself, preventing a phenomenon known as ratcheting, which is progressive structural distortion.
Let us ground this in a physical analogy for clarity. Mechanically speaking, we are talking about an intentional one-time calibration of the steel.
You could phrase it that way, yes.
It is akin to taking a brand new heavy-duty industrial spring and intentionally compressing it until it bottoms out once. It yields slightly, takes a permanent set or shape, but from that point forward, it operates perfectly elastically within its newly established operational range. Is that an accurate representation of the residual stress shield?
Yes, that perfectly illustrates the mechanics at play. The 3 S sub m threshold is the mathematical boundary that guarantees the spring can take that permanent set without breaking.
How does the math correlate to the yield strength?
The allowable stress, S sub m, is typically calibrated to 2/3 of the material's yield strength, S sub e. Therefore, a limit of 3 S sub m is roughly equal to 2 times the yield strength, or 2 S sub e.
And during the startup cycle?
During the very first operational cycle, a localized hotspot yields in tension. When the refiner unit cools down and the thermal load is removed, the vast surrounding area of colder elastic material acts like a clamp, forcing that localized yielded zone into a state of severe compressive residual stress.
So it preloads the joint in compression.
Exactly. On the next startup cycle, the operational thermal expansion must first overcome this deep residual compression before it can generate tensile stress. The net stress swing remains strictly within the 2 S sub e elastic recovery window, oscillating perfectly from negative yield to positive yield without ever tearing the metal.
Let me present a severe gut check on your analysis. If I'm the technical director reviewing your localized FEA plot right now, and the color gradient clearly indicates the stress at a junction has breached the material's yield strength, standard engineering intuition screams that the metal has failed.
I understand why one would think that.
You have crossed the yield point. Defend why I should not reject your design and order an immediate costly redesign.
Well, uh, rejecting the design purely because a localized point exceeds yield on an FEA plot represents a fundamental misunderstanding of displacement-controlled loads versus load-controlled loads.
Differentiate them for me.
If internal pressure, a load-controlled force, causes the entire wall to exceed yield, the vessel will continue to expand until it bursts. That is failure. But thermal expansion is displacement-controlled. It is self-limiting.
Because it only expands a set physical distance?
Right. The pipe or nozzle only wants to expand a specific physical distance, say half an inch. Once it expands that half inch, it stops pulling. Localized yielding under a self-limiting displacement load is completely acceptable, provided the 3 sub-m shakedown check is satisfied. The shakedown principle utilizes controlled initial localized yielding to build an internal residual stress shield, forcing all subsequent operational cycles to remain fully elastic.
And if your secondary stress breaches the 3 sub-m limit, explain the precise mechanics of the failure mode.
The failure mode is thermal ratcheting, culminating in low cycle fatigue rupture. If the stress range exceeds twice the yield strength, the material cannot shake down. It cannot establish a stable elastic loop.
So it just keeps yielding.
Exactly. Every single time the refinery unit starts up and shuts down, the metal undergoes incremental permanent plastic strain. It yields in tension, and then it yields again in compression. Over time, the material physically distorts, bulges, thins down at the discontinuity, and eventually fractures wide open.
Demand a real-world field application where we absolutely rely on this controlled yielding for long-term viability. Give me an example.
A prime application is the attachment weld of a cyclic coke drum skirt. Coke drums undergo violent thermal cycling, filling with boiling hydrocarbons, and then being quenched with water every single day.
Those are brutal thermal gradients.
Very brutal. During the startup sequence, the junction where the support scud is welded to the hot vessel shell experiences intense localized thermal gradients. The stresses here routinely reach 1.8 times the material's yield strength.
Almost double the yield point.
Right. If you evaluated this under basic load-controlled rules, you would assume the skirt is failing. However, because this stress is entirely displacement controlled by the vessel's thermal expansion and remains firmly under the 3 sub-m boundary, the skirt attachment safely shakes down after the first 2 process cycles.
So it takes that permanent set you mentioned.
Yes, and following that permanent set, it operates entirely elastically for decades without exhibiting progressive structural bulging.
Are there environmental constraints where this shakedown principle collapses completely, rendering your 3 sub-m math dangerously obsolete?
Yes, and this is a critical constraint. Shakedown tracking assumptions are completely dependent on the material possessing a stable, predictable yield point.
And when do we lose that stability?
If the vessel operates in the creep regime, at exceedingly high temperatures where the steel exhibits time-dependent creep or strain-softening behavior, the metal behaves more like slow-moving taffy under load.
So the elastic rules no longer apply.
The classic 3 sub-m elastic limit loses its validity completely. In these elevated temperature scenarios, relying on basic elastic shakedown is a lethal error. A rigorous elastic plastic or creep ratcheting simulation must be mandatory to ensure the vessel does not suffer progressive structural collapse over time.
Your grasp of localized vessel dynamics is well documented, but a perfectly engineered nozzle is entirely useless without a pipe attached to it. Let us scale up from the isolated vessel to the macro system. For the next technical inquiry, why can a standard ASME B16.5 flange fail catastrophically in service, spilling hydrocarbons even when operating completely within its listed pressure temperature ratings? And how exactly do external piping moments alter its sealing capability?
Well, the failure occurs due to a massive analytical blind spot inherent in standard flange ratings. ASME B16.5 standard pressure temperature rating tables are formulated with an isolated assumption.
Which is what?
They assume the flange joint is subjected only to internal fluid pressure and standard bolt preloads. The tables guarantee that the flange ring has sufficient thickness to contain the pressure bursting force.
But they ignore external forces.
They account for exactly 0 external piping loads. When connected to a refinery system, thousands of feet of piping act as long structural levers. When that system heats up to 600 degrees, the thermal expansion generates massive external bending moments and axial tensile shear forces that are driven directly into the flange assembly.
So, an ASME B16.5 rating essentially guarantees internal pressure containment, but high external piping expansion moments essentially act as a giant mechanical crowbar that will warp the gasket seating plane long before the nominal pressure rating is ever reached.
Precisely. The crowbar analogy perfectly isolates the mechanical action. When that external bending moment is applied, it creates a highly asymmetric load profile across the circular face of the flange.
Meaning, one side gets squeezed, the other gets pulled.
Right. The moment acts to compress the gasket tighter on one side, the pivot point of the crowbar, while simultaneously prying open the joint on the diametrically opposite side. This prying action physically stretches the bolts and unloads the compressive force on the gasket.
And the gasket needs that compression to seal.
Exactly. To contain highly pressurized fluids, a gasket must maintain a minimum compressive stress, defined as a multiple of the internal pressure, or M times P. If the external bending moment reduces the local gasket compression below that minimum threshold on the tension side of the joint, fluid containment fails immediately,
Regardless of what the internal pressure gauge reads.
regardless of the gauge.
Identifying the vulnerability is only half the job. How do we engineer a defense against it? Rather than dictating the raw algebraic formula, conceptually explain the mechanism of the Kellogg method. How does it bridge the gap between physical piping leverage and standard pressure tables?
Well, to defend against this, engineers utilize equivalent pressure verification via the Kellogg method. Because the standard ASME B16.5 tables only speak the language of internal pressure, we must translate the physical bending forces into that same language.
So we convert moments into an artificial pressure metric.
Right. The Kellogg method mathematically converts the external piping moments and axial forces pulling on the flange into an artificial supplementary equivalent pressure, or P sub eq.
Walk me through the formulation conceptually.
We calculate how much internal pressure it would take to create the same amount of longitudinal stress in the attached pipe, and we add that artificial number to the actual internal process design pressure. This combined total must fit within the maximum allowable pressure rating listed in the B16.5 tables.
And if it breaches the limit?
If the sum breaches the limit, the flange is deemed structurally incapable of resisting the piping leverage and will leak.
Demand the quantitative numbers for a failure scenario. Walk me through a specific design progression utilizing this translation.
Let us evaluate a standard class 300 flange operating at a process pressure of 18 bar. According to the B16.5 tables at the design temperature, this flange is rated to hold 38 bar.
So looking strictly at internal pressure, 18 bar is well below 38 bar. It looks safe on paper.
It looks completely robust. However, we must integrate the system reality. The piping stress engineering report reveals a massive thermal expansion bending moment resting on this nozzle connection.
So we run the Kellogg translation.
Right. We run the formula, and those external forces convert to an equivalent pressure of 24 bar. Now we sum the system. 18 bar of true internal pressure plus 24 bar of artificial equivalent pressure yields a combined load of 42 bar.
Which obviously breaches the 38 bar limit.
Exactly. This combined reality of 42 bars significantly exceeds the flange's structural limit. The data forces the engineering team to discard the initial specification and upgrade the entire connection to a thicker, stiffer Class 600 flange assembly.
Ensuring the joint possesses the mechanical rigidity to resist the piping leverage without unloading the gasket.
That is the architectural logic, yes.
Is the Kellogg methodology universally reliable as a screening tool across all refining infrastructure?
No, and applying it blindly is a severe engineering hazard. The primary detailed caution here is that Kellogg's formulation fundamentally treats the flange ring as a completely rigid, unbending body.
It ignores the elastic flexibility of the flange itself.
It completely ignores it. While it is an excellent conservative screening tool for standard sizes, when evaluating equivalent pressure on high-temperature critical joints or large-diameter flanges, specifically those greater than 24 inches, Kellogg's assumption of rigidity becomes highly unconservative.
Because large flanges will physically warp.
Right. Large-diameter flanges will physically warp and dish under external moments long before Kellogg's linear math predicts failure. For these critical massive joints, engineers must escalate beyond the Kellogg approximation and deploy ASME Section 8 Division 1 Appendix BFJ. Or they must execute localized finite element analysis to ensure the actual bolt stress and gasket seating stress remain secure during extreme thermal transients.
Your architectural logic is sound, candidate. Your
Yeah.
ability to bridge complex code theory with uncompromising physical field mechanics demonstrates the exact level of accountability required for high-stakes engineering. The technical assessment is now formally concluded.
Thank you.
We're going to look at an entirely new ecosystem designed specifically for working professionals to help you master those high-pressure moments. Okay, picture this. You're sitting right across the table from a panel of... They aren't asking about your hobbies anymore. They're dropping you directly into the hot seat to test your true operational readiness. Imagine you're in that interview. The pressure's on. You're facing intense, high-stakes scenarios. In a real-world interview, you need something that prepares you for the absolute reality of the industry, where your split-second engineering decisions have massive financial and, of course, safety implications. And that brings us to this absolutely game-changing app, which is available right now on the Play Store. What we're looking at here isn't just some random list of questions thrown together. No way. It is an exhaustively structured solution. It provides AI-driven, highly practical, example-based Q&As that form a comprehensive framework. Because the sheer scale of this architecture is massive. We're talking about a structure spanning over 200 sections, and it caters to everyone, beginners, intermediate folks, all the way up to experienced and expert professionals. The rule of thumb here is simple. If it's in the plant, it is in this app. It really acts as a complete pedagogical roadmap for your entire career. Now, you might be wondering, how does it deliver all this content without getting super repetitive? Well, the core of this app is what they call the Studio Engine. It's this AI powerhouse that entirely eliminates the limitation of predetermined static questions. Instead, it dynamically generates a highly structured, unlimited repository of practical Q&As right when you need them. So by doing this, it actually tailors a dynamic mock interview simulator specifically to your current knowledge gaps. It brilliantly illustrates how concepts are queued sequentially. You just select your domain, your section, and then your concept, and the app continuously feeds you the next logical scenario. Because getting a question is one thing. Understanding the multidimensional answer is a whole other ballgame. The system doesn't just feed you a wall of text. Every single generated response is deconstructed into 5 distinct steps. It actively highlights the critical responses you absolutely must deliver and warns you of the hidden pitfalls. Now, they represent only a minor part of the unlimited Q&As available in the app, but they serve a very specific, crucial purpose. They perfectly simulate real-world office arguments, differing viewpoints, and intense technical debates. Because let's face it, engineering isn't just taking a test in a vacuum, right? It's about navigating heated arguments and proving your technical acumen when challenged by your peers or your superiors. And a massive part of these sessions is the power of roleplay. After every mock interview section, videos feature AI-generated live roleplay interview sessions complete with feedback on pertinent domain subjects. Giving real roleplay interviews after enriched technical discussions acts like an incredible catalyst. It is a tremendous confidence booster for any aspiring candidate, consolidating everything you've learned into practical, real-world readiness. Which leaves us with one final, very important thought. What step are you going to take right now to engineer your own success? Mastering your craft is a lifelong pursuit, and with tools like this at your fingertips, the depth of your knowledge truly has no limits. I highly encourage you to check out this combined integration of texts, text-to-speech audio, videos, and live role-play interview sessions. The tools are definitely out there to unlock your potential. The only question is, are you ready to use them?